This is going to be the part of the lecture series on numerical in algebra, and in this video we are going to see about the way to compute the eigenvalues for the dense matrices. It involves two phases. The first phase is to reduce the dense matrix to a specialized structured form like called a Heisenberg form, which we'll be discussing later. And the second phase would be an iterative process to compute the eigenvalues, where the iterative process converges to computing the eigenvalues when the convergence tends to infinity. So this computing the eigenvalues have a very difficulty in two aspects. One is we saw in earlier that the eigenvalues are the roots of the characteristic polynomial, and we also saw in the earlier lectures that computing the roots of a polynomial using a numerical algorithm is an ill-conditioned problems. So it's a very ill-conditioned problem. It tends to instability. So the second fundamental difficulty is related to how the way related to this theorem. So when the characteristic polynomial of degree is greater than or equal to 5 with rational coefficients, then there is no any mathematical expressions to explicitly to state the roots of the polynomial for the corresponding polynomial equations for which the degree is greater than or equal to 5. It means that we cannot closely express the roots of the polynomial for which the polynomial degree is greater than or equal to 5 in a closed form. So it can be only in an approximate solutions to identify the roots of the characteristic polynomial of degree greater than 5. So this theorem was identified during the time of so around 19th early part of the 19th century by two young mathematicians called Abel and Galice. And what they identified and proved is no analog of the quadratic formula can exist for polynomials of degree 5 or more. So these two difficulties, one is the difficulty with respect to the way we are computing the eigenvalues, because the root finding problem itself and ill conditions in fixed point arithmetic. And the second is there is no explicit mathematical expressions to exactly calculate the roots of the polynomial of degree greater than or equal to 5. So these two things, although we involved in finding the eigenvalues of the dense matrices, in earlier lecture series you see that for dense matrices for a linear system of equation there is a fixed finite number of steps. That it means that there is a direct method to compute the solutions for the linear system of equations. But for the eigenvalue equations, and even though the matrices are involved in dense, there is no finite number of steps to compute the eigenvalues because of this because of this main difficulty. And since because of this theorem 25.1, any eigenvalue solver has to be only iterative. There is no any direct method or a fixed number of steps to be involved to find the eigenvalue exactly. So it has to be iterative, and in order to get the exact solution, that iterative has to tend towards the infinity. But unfortunately many of the iterative algorithms have a great convergence. So uh, uh, so it can be the eigenvalues for any matrix can be computed with a reasonable accuracy with a finite number of iterative steps. So with this conclusions, and with the last lecture we saw that there are three ways of factorizations where eigenvalues can be computed. Only as we remember, those three factorizations can be first is diagonalization, that is eigenvalue decompositions. Second is unitary diagonalizations, and third is unitary triangulations. So eigenvalue decompositions can be done only if provided the transform matrix X is non-defective. Unitary diagonalization can be done only if the matrix involved A is normal matrix, and a skew decomposition like unitary triangulation can be done for any matrix. So since it doesn't require any specialized conditions, Uh, then unitary triangulation, skew factorizations will be involved in computing the eigenvalues. But but there is a specialized thing. We know that this is a skew factorization, which involves a sequence of unitary transformations where the A is transformed to a triangular upper triangular matrix as J tends to infinity, and the eigenvalues can be computed along the diagonal values of the transformed triangular matrix. If it is a Hermitian, then it will be end up in a unit Hermitian diagonal, that is called as a Hermitian triangulation, that is called as a diagonal matrix. So this iterative process for the dense matrix eigenvalue computations involve two stages. One is to transform into a specialized matrix for Heisenberg matrix, and the second one is, as we mentioned earlier, there will be a sequence of iterative transformations so that it will be end up into a tridiagonal matrix, and the eigenvalues can be computed along these diagonal values. So, what is the reason for us to go for this Heisenberg transformations, and then we had to be involved in this one will be revealed in the next part of the video. But we can see that operating count through this operating count, we can understand that why the first phase is very important. The first phase is involve m cube flops, and the second phase involve each iteration involve around m square flops, and it takes m iterations, though it has m cube flops. But in case if you do not have this first phase transformations, then the second phase and each and every iterations would be involving around m cube flops. So it will be in one order of magnitude one higher than the previous two-stage process. So that is the one of the reasons that where we require two-stage process. One is to convert into a Heisenberg matrix. Then the second stage would be to make a sequence of transformations to end up in a triangular matrix. If it is Hermitian, then it will be end up in a tridiagonal matrix. Hermitian Heisenberg matrix will be a tridiagonal, and Hermitian triangular matrix will be a diagonal matrix. Hopefully, we'll see about how to compute the Heisenberg matrix and the tridiagonal matrix in the later part of the lecture series. Thank you.